Hello everyone, my name is Niklas Haag and the topic of my presentation is the Dueling network architecture, which was proposed by the Google DeepMind team around Zio Wang. I will first do a quick recap on very basic background knowledge before I go into the new Dueling network architecture and explain why it is different to the single stream networks that were used prior to this paper. I will also explain what it does better and why it works. Afterwards, I will go into the experiments that were conducted to evaluate this new architecture and finally summarize things in a final conclusion. The two most essential functions in reinforcement learning are the state value function, which calculates how high the expected discounted return is an agent can expect to receive when it is located in a specific state S, and the Q function, which calculates how high the expected discounted return is an agent can expect to receive when it is located in a specific state S and chooses to perform a specific action A. It can be observed that the difference between Q values is often very low in comparison to their magnitude, and this was also noticed by the authors. And they introduced a new function which they called the advantage function. The advantage function is calculated by subtracting the state value from the Q values, and the result is a so-called advantage value. And the advantage value for an action basically says how good or how important the action is in comparison to the other actions that are possible from the state. I also want to quickly touch on double Q learning because this is the algorithm that was used to train the networks during the experimental stage of this paper. The main benefit from double Q learning is that it mitigates the problem of overestimating Q values, and this is done by using two sets of parameters. So these two thetas are different sets of parameters, and one set of parameters is used to make or to choose the best possible action, and the other set of parameters is then used to evaluate the action that was chosen by the first set of parameters, and this actually leads to a better approximation of the Q values. If one closely looks at common reinforcement learning problems, one can observe that in many cases there are multiple actions that, if performed from a specific state, really don't change the environment in a meaningful way. An example for that is shown on the right. This is a screenshot from the game Enduro. And the goal of the game is to dodge incoming enemies. The thing is, as long as there is no enemy right in front of the player, it really doesn't matter whether the player moves left or right. These actions only become important as soon as there is an enemy actually approaching the player. The dueling network architecture learns a state value which is shared across the actions in a state, and therefore enables faster learning, faster conversions. And I will now go into how this works exactly. The new feature of the dueling network architecture is that at some point the network splits into two streams. Here at the right you can see two networks. The one at the top is a simple single stream network, while the one at the bottom is the new dueling network architecture, which splits into these two streams. The stream at the top is the state value stream, which estimates the state value function, and therefore only has a single output unit, which represents the estimated state value, while the other stream, this one right here, estimates the advantage function and has as many output units as there are possible actions the agent can take, which results in a single estimated advantage value for each action. The outputs of these two streams are then combined using a so-called aggregating module, which then outputs the final estimated Q values. Obviously, also a single estimated Q value for each action. The main benefit to using these two streams is that during temporal difference learning, only a single action actually contributes to the update during backpropagation. And by using these two streams, with every update, the state value function is updated, and therefore this architecture should lead to faster convergence when there is a problem with a large number of possible actions. So in summary, the dueling architecture makes use of two separate streams, which estimate the state value function and the advantage function respectively. The question now is how the outputs of these two streams are combined to form the final Q values. And it turns out that one cannot just use the most naive way to solve this, but one has to actually put a little more thought into this. The most naive design for the aggregating module would be to just look at the definition of the advantage and derive the calculation of the Q values from that. And this would then lead to the sum of the state values of the state value and the single advantage values. Just for clarification, the theta are the parameters that both streams share. So for example, the parameters of the convolutional feature extraction module before the network splits, while the alpha are the parameters from the advantage stream, while the beta are the parameters from the value stream. However, using this function for the calculation of the Q values is bad for two reasons. First of all, there really is no guarantee that V and A are in fact good approximators for their respective function. And therefore it would be very brave to just add them up and hope for the best. The second problem is that using this function, given Q, you couldn't reconstruct V and A. So for example, if you have a Q value and add a constant to the advantage stream and subtract the same constant from the value stream, you would again end up with the same Q value. And this was shown by the authors to lead to very poor performance, and therefore they had to design the aggregating module differently. There are two solutions to the reconstruction problem. The first solution forces the advantage stream to have an advantage of 0 for the best action. This is achieved using this term right here. So the maximum advantage value is subtracted from all the advantage values, and the results of this subtraction are then added to the value, the state value. And after this forward mapping, the Q value of the best action is actually equal to the state value, and this makes it very, very easy to separate the two streams. The alternative solution substitutes the max operator by an averaging operator. So the average of all advantage values is subtracted from the advantage values, which results in values centered around 0, and these are then added to the value to the state value. This also solves the problem, but by doing this one loses the original semantics of the value function and the advantage function, because they are basically both off target by a constant. But it was found that this solution increases the stability during training, and therefore this was also the solution that the authors used in the experiments that they conducted later. Since the aggregating module basically only performs additions and subtractions of constants, it is always sufficient to evaluate the output of the advantage stream when choosing an action, because this leads to the same action one would get if the final Q values were evaluated. It is also very important to notice that the aggregating module is implemented as a part of the network and not as a separate algorithmic step, and therefore the only thing that is needed to train the network is the backpropagation algorithm, which is very convenient because the Dueling network architecture can then be combined with other techniques and methods that were already proposed and were shown to improve the overall performance of DQNs. And this probably will also hold for future methods and techniques. In order to evaluate the performance of the new network architecture, the authors used two separate environments. The first one was a very simple self-made environment they called the corridor environment, while the second environment was the arcade learning environment, which was also used to evaluate several other reinforcement learning algorithms, and therefore was a good basis for comparison to other approaches. In the corridor environment, the agent starts at the position indicated by the star and has to move to the top right in order to get the highest reward. However, also the lighter red colored position terminates the episode, but obviously the reward isn't as high as in the other red position. There are 20 states vertically and 50 states horizontally, and the actions the agent can take are move up, move down, move left, move right, and a no operation. So the agent would just perform no action at all. The training in the corridor environment was done using the TD0 algorithm with an epsilon greedy policy with epsilon set to 0.001, so the agent had the chance of 0.1% to choose a random action from the possible actions. They used the update rule of expected sarsa to minimize the cost function, which is shown right here. And in order to measure the performance, they calculated the squared error against the two state values. The performance of the dueling network in the corridor environment was then compared to the performance of a very simple single stream multilayer perceptron, which is shown right here. So the single stream network basically has 3 fully connected layers with 50 units each, while the dueling architecture starts with a fully connected layer of 50 units and then splits into value stream and advantage stream, which both start with 2 fully connected layers with 25 units each. You can instantly see that these networks roughly have the same number of parameters, and therefore this should make a viable comparison. These two networks were then trained in 3 different scenarios. The first one is shown over here, which basically is the experimental setup that I already mentioned before. So the agent has these 5 actions: going up, going down, going left, going right, and the single no operation. And it is already visible that the dueling network converges faster. These are the error curves, by the way. The second scenario was then created by adding 5 more no operations to the pool of possible actions the agent can take. So the possible actions were then going up, going down, moving left, moving right, and 6 no operations. And this is where the benefit of the dual stream architecture comes into play, because it now is really visible that the network converges faster, and this should be due to the fact that every single update also updates the state value function, and therefore the state value function can be learned very efficiently, and this is underlined by the third scenario, where there were 16 no operations in total. So one can definitely say that the dueling architecture adds a whole lot of performance to this. This is definitely also very useful in practical settings, because in practical settings there are oftentimes problems with very many actions, and therefore the improved learning capability of the network regarding the state value function really should improve the performance in these scenarios. The second environment used to evaluate the performance of the new architecture was the arcade learning environment, which was also mentioned in previous presentations. The challenge there is to deploy a network with fixed algorithm, fixed architecture, and fixed hyperparameters to learn 57 Atari games. They compared their results to the results that Van Hasselt et al. Achieved in 2015 and used the DDQN algorithm to train their network. Because the layer before the splitting into 2 streams receives basically receives gradients from 2 sources, being the 2 streams, the authors introduced a rescaling of the gradient by a factor of 1 over square root of 2, which is a simple heuristic which slightly increases stability during training. They also perform gradient clipping to a norm of lesser or equal than 10 and use the ReLU activation function between layers. In order to isolate the contributions from the dueling architecture, the authors of the paper trained 2 separate networks, with one being the dueling network and the other one being a simple single stream network. It is worth noting that these 2 networks roughly have the same number of parameters in order to make this a viable comparison. The agent was initialized in a random starting position at the start of an episode, and the performance of an agent was calculated according to this formula, with the score baseline being the score that was achieved by the network of Van Hasselt, and the score at random being a score that an agent would achieve that uniformly chooses random actions. These are the results of the comparison between the performances of various network architectures and algorithms. One can clearly see that the dual clip method, which is the dueling network with gradient clipping, performs substantially better than the single version, which is the network that was used by Van Hasselt in 2015, and the dual clip version also performs better than the single clip version, which is the network that was previously shown, basically the dual clip version, but in the single stream variant. And on the right you can see that The graphic on the right shows the comparison between the dual clip version and the baseline network, which is referred to as single in this table, and it is clearly visible that in most cases the dual clip version significantly outperforms the network proposed by Van Hasselt. In summary, the dual clip version achieves human level performance in 42 of 57 games, which is pretty good. And it was also found that the performance benefit from using the dueling architecture does indeed grow with the number of actions that the agent can choose. It is, however, a problem that these Atari games are of deterministic nature, and therefore it was possible that the agents wouldn't really learn to play the game, but only remember sequences of actions that would lead them to a high reward or to a high score. And therefore the human starts category was introduced. For each game, 100 starting points were sampled from a human's trajectory, and these 100 starting points were then used to initialize the agents. And only rewards that were accumulated after this initialization were then used for the training process. And by this, the authors were hoping to mitigate this problem of trajectory learning. The performance percentages from these human starts are shown here in the right column, and one can again see that the dual clip version significantly outperforms the single clip and the single version, and the nature DQN, which is the original DQN proposed by Mani et al. In 2015, really is outperformed in an even more significant way. One very convenient thing about the new architecture is that it is trained basically just like any other DQN, using the backpropagation algorithm, and therefore it is very easy to combine it with methods and techniques that were previously proposed and shown to increase the performance of DQNs. And one of these techniques is the prioritized experience replay, which was proposed by Scholl et al. In 2016. And the authors also included this prioritized experience replay in their experiments in order to see how their new architecture and this method would interact and improve the performance even further. And they used the rank-based prioritized sampling for this. The results of these runs are shown in this table at the top. So the prioritized dual clip being the dueling network with gradient clipping and the prioritized experience replay included. And you can clearly see that this version outperforms all the others. Also the prioritized single version, which is the network that was used and trained by Van Hasselt in 2015. So you can definitely say that the dueling architecture adds a whole lot of performance to this already pretty well performing network. Here on the right is a more detailed comparison between the prioritized dual clip version and the network trained by Van Hasselt. And again, the performance gain from the dueling network architecture is clearly visible, especially in these games right here. So there is a very significant improvement visible. In order to determine which regions of the input images were especially important for the network, the authors computed the so-called Salience Maps, and these are shown on the right in these red regions. And it is very interesting to see that while there is no enemy right in front of the player, the advantage stream doesn't really pay attention to much at all in the image, while the value stream evaluates the current state the player is in by looking at the road. However, as soon as enemies approach the player, the advantage stream looks at them and recognizes them and makes the decision accordingly to dodge the enemy. If one looks at the performance scores of single stream network and dueling network, one can definitely think about whether there are drawbacks that come with the dueling network architecture. But since in all of the experiments conducted in this paper, the authors made sure that that single stream network and dueling network always had roughly the same number of parameters, and the dueling network still outperformed the single stream network in every case. There don't really seem to be any drawbacks to using this architecture. In summary, the use of the dueling architecture oftentimes results in a faster convergence, which is due to the fact that with every single update, the value stream is also updated. So the architecture allocates more resources to the value stream than single stream architectures do. And this allows a very efficient learning of the value function, which is overall very beneficial for the overall training process. The dueling architecture is very useful in environments with a high number of actions because since the state value function is trained or is learned separately, the network can essentially generalize across actions with the same or with similar values. Another benefit from this architecture is that it is basically trained like any other DQN just by using backpropagation, and therefore it allows an easy combination with previously proposed methods like prioritized experience replay and probably also methods that will come up in the future. And finally, there don't really seem to be any major drawbacks because in all the experiments the authors made sure that the single stream network and the dueling network both had roughly the same number of parameters, and still the dueling network outperformed the single stream network in every case.